Again, welcome to Mathematics 164 Precalculus. This is lecture 6-2, which cover chapter 6, section 2 of our course textbook. In these lectures, we're going to cover the compound interest and also geometric sequence. So our main objective is to find the future value of a compound interest investment and also the amount of interest earned when interest is compounded at regular intervals or continuously. We're also going to learn how to find the annual percentage yield, which is APY, or the effective annual interest rate of money invested at compound interest. We're also going to learn how to find the time it takes for an investment to reach a specified amount. Also to find the specified terms and sums of a specified number of terms, and also geometric sequences. So first we start with the compound interest. Here we say the compound interest is the second method of paying interest. And the first method was the simple interest. Now the difference between simple interest and compound interest is that with simple interest, when we earn interest, we are not going to add it to the principal amount. We are going to withdraw it. So the amount invested will stay the same, constant throughout the period of the investment. But with compound interest, we add the interest to the principal. So as time progresses, and the principal amount increases, and this will lead to yield more interest. So each interest is added to the principal. So here we say with compound interest, both the interest added and the principal and interest for the next period. So with this method, the principal grows as the interest is added to it, which is again opposite for simple interest. Simple interest, we withdraw the interest. We don't add the interest to the principal. So the principal amount remains constant throughout the period of the investment. Again, with compound, again, the principal amount increases as we add the previous interest to the principal amount. So the concept of future value, which is the annual compounding, is that if we have S dollars or we have dollars of P, and the P dollar is invested at the interest rate of R per year, then compounded annually, the future value S at the end of the 9th year is S equal to P bracket 1 plus R to the power N. So again, S will be our future amount. Now with simple interest, the first thing we need to do is to find the interest amount for the period of the investment. Then we are going to add that interest to our principal, and that will give us our future amount. But with again compound interest, the formula is again the principal 1 plus R. R will be the rate, the interest rate to the power N. And N will be the number of years. So let's see one example. Here they say we should find an annual or future investment amount. For now, we have $3,000 is invested for 4 years. So N is 4 at 9% compounded annually. So we have again 0.09 interest rate. So to find the future value, it will be 3,000, which is our P, the amount we invested, 1 plus R. R is the interest rate, which is 9%. And that will be 0.09 to the power N. N is always in years, the time in years. Here is 4 years, so to the power 4. So our answer for the future amount will give us $4,234.7448. Roughly, we say $4,234.74. Now, this will be the future value. Now, to find, the question is how much interest is earned. So to find how much interest is earned, we are going to subtract the principal amount from the future value, and that will give us, again, our amount. So this is the future value. So now we subtract the future value minus the principal investment. So this means our interest for the period of 4 years, 9% will be $1,234.74. Let's go back to the example one more time. So the question here says, we are investing $3,000 for 4 years. Our interest rate is 0.09 or 9%. How much interest we earn? So the first thing we do is to find the future amount, which is X, and always S equal to the principal amount, 1 plus the rate R to the power N. So we have 3,001 plus 0.09 because 9% is 0.09. So it will be 1 plus 0.09 to the power 4. When we do our 1 plus 0.09 will give us 1.09. 1.09 to the power 4 will give us 1.411586. Then we multiply it by 3,000, and that gives us $4,234.7448. So roughly we say $4,234.74. Again, this amount is the future amount. Our question said we should find the interest. So we are going to subtract the future amount minus the principal amount. So the answer will be $1,234.74. So here we say some accounts have the interest compounded semi-annually, quarterly, monthly, or daily. Now, annually, N will give us, if it's 1 year, N is 1. If it's semi-annually, then N will be half. If it's quarterly, then N will be 1 quarter. If it's monthly, then 1 over 12. 12 months is 1 year. And daily, 1 over 365. Because again, in the financial industry, banking, interest is always, the rate is in yearly. So if I invest the money in the bank for any amount of money, my interest again is calculated yearly. But they can compound it monthly, it's up to the bank. So in this case, if it's monthly, the period will be 1 over 12. So here we say, unless specifically stated otherwise, the stated interest rate called the nominal annual. So annual means it will be per year rate. So it's the rate per year and it's donated by R. So in our calculation, as we saw in the first example, again, R is in the rate. 9% means 9% annually. For 4 years means we get 9% annually for 4 years. But again, if it's stated that semi-annually, then the N will be half of it. So if it's yearly, N is 1. Depends how many years. Quarterly, as we said, 1 quarter. Monthly, how many months we have in a year? 12 months. Daily, how many days we have in a year? 365. So it will be 1 over 365. That will give me the interest N per day. So again, the interest rate per period donated by I is the nominal rate divided by the number of interest period per year. So as we said, if it's daily, the interest period will be 365 days a year. If it's monthly, we have 12. So 1 over 12 period. So the interest period are also called the conversion period. And the normal period, again, is donated by N, as we saw the example. So let's look this question. So for example, if we have $100 and $100 is invested for 5 years at 6% compounded semi-annually, which is twice a year, then it has been invested for 10 periods. It's 5 years. So if it's 5 years, semi-annually means half a year. So we're going to get semi-annually 5 years will be 10. Because we say 5 years times 2 periods per year. The same thing if it's monthly, then times 12. So in this case, we can find the interest to be I equal to 3%. So if we use 3%, then we are going to use N equal to whatever the amount here, 10. So we can write again the 5. So we have two options. We can leave the 6% and we can say the n will be 5 divided by 2 because it's semi-annually. Or we use 3%, then we use our 5 there. So this is the formula if a specific period is given. So the future value of an investment of this type is found using the following formula. First, we know that if P is invested for T years at a nominal interest rate, compounded annually, we saw that formula already. Here we are going to say compounded M times per year. So it can be semi-annually, quarterly, etc. So the first thing that we need to do is to find the total number of compounding period, which is n equal to MT. So when it's semi-annually, if it's 5 years, then 5 times 2, because semi is 2 twice. Quarterly means we get 4 per year, so 4 times the year. So the interest rate per compounding period is now I equal to R divided by M. So if it's 6% now, it will be, if it's semi-annually, then it will be 6% divided by 2. If it's quarterly, 6% divided by 4. So we can substitute the N and I in our formula. So we know original formula again is S equal to P 1 plus R to the power N. So S equal to P 1 plus R to the power N, as we said earlier before. But compounded annually, our interest rate, we say R over M. So we represent it as R over M. Then we also said that, again, if it's not annually, then whatever M is, so M times T. So again, the interest rate will reduce, depend. If it's 6% annually, then semi-annually will be 3%. And if the time is 2 years, semi-annually will be what? 2 times 3 years, or whatever the year. So let's see an example. So example is given to us here. Here they say Jim and Eddie want to have 200,000 in Morris College Fund on her 18th birthday. And they want to know the impact on this goal of having $10,000 invested at 9.8% compounded quarterly on her first birthday. So to advise Jim and Eddie regarding this, we need to find the future value of the $10,000 investment and also the amount of compounded interest that the investment earns, and also the impact this will have on their goal. So we know the principal amount is given to us. Here they say Jim and Eddie want to have this amount on an 18th birthday, and they want to know the impact on this goal of having 10,000 invested. So we have the $10,000 principal, the future amount 200,000, the rate is given. So now for this calculation, I equal to, again, the interest rate is 9.8 and also compounded quarterly, so it's 4. So this means I equal to 0.098 divided by 4. So our interest rate will be for compound quarterly with 0.0245. And also N will be 4 times 17, because when we look at the question, it's already first year. Their child is first year, but 18 from 1 year to 18 is 17 years. So here they say on her first birthday, they are going to start the investment until they the child reach 18. So this means N is 17. But since it's compound quarterly, we say 4 times 17 is 68. So now we can be able to find S equal to P I plus 1 to the power N, which is Our 10,000 is given. We have 1 plus. I will be 0.0245, which is 0.098 divided by 4 because it's quarterly. And also our N will be 17 years since it's quarterly multiplied by 4. So we get 68. So if we use the calculator, and our final result will be 51,857.70 cents. Now our amount of interest earned is 51,857.70 cents minus the actual amount that we invested. So we have 41,857.70 cents. So that will be the interest we are going to earn again in the period of 17 years. Now, C said we want to know the impact. So $10,000 was invested by Moray's first birthday, which grows to an amount that is slightly more than 25% of their goal. Again, their goal was, I think, $200,000. So they want 200,000. By looking at this investment, again, we have amount of 51,857.70 cents. So roughly we say 25% of their goal. So this rather large earlier investment has a substantial impact on their goal. So most likely they need to invest more money. So yeah, we said that if we invest a sum of money, say $100, then the higher the interest rate, the greater the future value. So the figure shows here a graphical comparison of a future value when $100 is invested, first at 5%, so we can see it grows slowly, then at 10%, then at 8%, then 10% more higher. Also, we should know that a higher interest rate will yield consistently higher future values, and also it will have a dramatically higher future values after 15 to 20 years. We should also note that these graphs of the future values are called the growth exponentials. Now, in order to determine the interest that results from continuous compounding, which is compounding every instant, we should consider an investment of $1 for 1 year at 100% interest rate. So here we can see if the interest is compounded m times per year, then the future value is given by the formula S equal to 1 plus 1 over m to the power m. So the table here shows the future value that results as a number of compounding period increase. So we start with 1 annually. We have 1 plus 1 over 1 to the power 1, we have 2. Then monthly will be 2.6130. Daily, we can see again the difference are not that much, but we can see that if a bank compound daily or even each minute, you are going to earn more interest than if it's monthly or semi-annually, etc. So again, the table shows that as the number of period per year increases, of course, the future value also will increase, although not very rapidly. Again, just a slight differences. And so if you invest money in the bank and they give you compounded interest monthly, it's better than semi-annually or annually. So here we say, in fact, no matter how often the interest is compounded, the future value would never exceed 2.72. So that's exponential, 2.718281. Then we got another 1818. Now the future value, here we are dealing with continuous compounding. In general, if $P is invested for 10 years at a nominal rate R and is compounded continuously, previously we did compounded in a specific period of time. Let's say compounded annually, compounded semi-annually, daily, monthly, minutes. But now the last option is compounded continuously. Remember the exponential here, the example we were given, if it's compounded even each minute, each seconds, hardly before it will reach 2.72, it will end up at exponential value, which is 2.71828, which will be even if it's every second. So if it's continuously compounded, we can see that instead of saying 1 plus r to the power n, we are going to represent e, the exponential value. So again, compounded continuously, the future value will be s equal to p exponential to the power rate times the time. The interest rate is r and the period of time is t. So here we have example. They say we should find the value or the future value if 1,000 is invested for 20 years at 8% compounded continuously. So if it's continuously, our formula will be again P times E to the power RT. Now let's see, invested for 20 years. So we have our T, interest rate also is given, which is 8%. And the principal is given, so we can be able to find the future value. So we have our P value again, 1,000, E to the power, the rate, 8% is 0.08. The years is 20. So we have 1,000 e to the power 1.6. We use our calculator to find e to the power 1.6, then we multiply by 1,000. So our final answer will be $4,953.03. Then we can also do the B. The B says so for the present value P in 25,000. So let's look at the question again. What amount must be invested? So we want to know the amount that will be invested, the P value, at 6%, which compounded continuously, so that our future value will be $25,000 after 8 years. So this means we know that time period 8 years, and also the rate was 6.5, so that is 0.065. To E, we don't know P, what amount we have to invest, but our future value is given. We want to get 25,000. So here we are going to do the formula transformation. When we use the calculator here, again, we get e to the power 0.52 will give us 1.68202 and 765. So 25,000 equal to P times 1.68202.765. The P again is multiplied by the value 1.68202.765. So to get P, we are going to divide it with 25,000. So P equal to 25,000 divided by 1.6820765. And that gives us roughly $14,863.01. So this means we need to invest $14,863.01 in 8 years with interest rate given to be 6.5% in order to get 25,000. So we have the concept of annual percent yield. So for example, suppose $1 is invested for 1 year at 8% compounded semi-annually. Then I will give me 0.08 divided by 2 because semi-annually. And also N will be 2 because it's 1 year, and semi-annually will be 2 times 1, so N is 2. So in this case, to find the future value, it will be $1, which is our principal amount, times 1.04 to the power 2, which will give us 1.08 0.0816. And the interest earned for this year is 1.0816 minus $1, which gives us 0.0816. One thing we should note that this amount of interest will represent an annual percent yield of 8.16. So we say that 8% compounded semi-annually has an annual percent yield or effective annual rate of 8.16. Similarly also, if $1 is invested at 8% compounded continuously, then the interest earned is $1 e to the power 0.08 and minus $1. So the interest will be 0.0833, which will be roughly APY of 8.33%. So in general, we will say that annual percent yield always equal to I by P, or just I if P equal to 1. So we can calculate APY with the following formulas. So let R represent the annual nominal interest rate for an investment. Then the annual percentage yield is found as following. We have the periodic compounding. That's if M is the number of compounding periods per year, then I will be R divided by M, and is the interest rate per period. So APY will give it 1 plus R divided by M to the power M minus 1. So it will be 1 plus I to the power M minus 1. R by M again is I. Now, continuous compounding, then APY will give us E to the power R minus 1, because again, the dollar is 1, P is 1, so E to the power R minus 1. Now we have another question saying, suppose a young couple, such as Jim and Eddie, from our application preview, found 3 different investment companies that offer college savings plans. The first one is one at 10% compounded annually, another at 9.8% compounded quarterly, and the third at 9.65% compounded continuously. We should find the annual percent yield for each of these 3 plans to discover which plan is the best. So API may tell us which of these 3 plans are the best. So let's start with the A. For annual compounded, the stated rate is the API, because this is annually compounded. So the API will be 10%. The rate is this because it's compounded only once a year. API is for once a year concept. Now, because the number of period per year is M equal to 4, which is quarterly, and the nominal rate or the interest rate is 0.098, then the rate per period is I divided by M, which will give us 0.098 divided by 4, and that will give us 0.0245. So the API will be 1 plus 0.0245 to the power 4 minus 1. Again, use the calculator, and we get 0.10166. So this will give us roughly 10.166% API. Now we have C. C, we say continuously, so we are going to use the formula E to the power of the rate. The rate is 9.65, so it will be 0.0965 minus 1. So we use the calculator. E to the power 0.0965 will give us 1.10131 minus 1. So that will give us roughly 10.131%. So we can see the difference. So far, we have 10.166 as the best, which is the B. This gives us 10.13. So hence we say that of these 3 choices, The 9.8 compounded quarterly is the best because that gave us 10.166, the B. So next we go to the geometric sequences. So in geometric sequences, we say that if $P is invested at an interest rate of I per period and compounded at the end of each period, then the future value at the end of each succeeding period is P. The first period will be 1 plus I. Second will be 1 plus I squared. Third will be 1 plus I cubed. As the period increases, the exponent increase. And this is the idea of geometric sequence. Arithmetic sequence, if we remember, we always do addition, subtraction to find the sequence. In geometric sequence, we do mostly multiplication. In this case, multiply by itself. So the future values of each of the succeeding periods form a sequence in which each term after the first term is found by multiplying the previous term by the same number. Such a sequence again is called a geometric sequence. So let's see an example. And before that, this is the definition. The sequence is called a geometric sequence or progression if there exists a number R called a common ratio such that we can say the R will multiply the previous value. So AN minus 1 is the previous value and AN is the present value. So to find the present value, we multiply R by the previous value. So now to get the next value, I'll multiply the R by the present value and that will give me the next value, which is the same as the previous example. So the formula for the 9th term of a geometric sequence is as follows. So we have AN will be A1, the first term, R to the power N minus 1. N is the nth term. So if it's 9th or let's say 5th term, which is A5, then it will be the A1, the first value, the R to the power 5 minus 1. So let's see an example here. Here they say we should find the 7th term of a geometric sequence with first term 5 and the common ratio, which is R, was -2. So we are looking for the 7th term. So that will be A7 equal to, the first term is 5, so equal to 5. So A7 equal to 5 times R. R is -2 to the power N minus 1. 7th term, so N is 7, 7 minus 1. So the answer will be 5 times 64, because we get an even exponent, -2 to the power 6. The negative will turn to positive because the exponent is even number 6. So 2 to the power 6 will give us 64. Then 5 times 64 will give us 320. So we also have the sum of geometric sequence. Same concept as the sum of arithmetic sequence. So the sum of a geometric sequence, we say the sum of the first n terms of a geometric sequence with the first term and also the common ratio is Sn, A1, which is the first term, times 1 minus R, the common ratio to the power n, the n term, divided by 1 minus R. Provided R is not equal to 1, because if R is equal to 1, the denominator value will be 0. You cannot divide a value by 0. This is a real number, so we don't get answer. So let's see an example. Find the sum of the first 5 terms of a geometric progression with the first term 4 and the common ratio is -3. So we have everything we need in our formula to find again the sum of geometric sequence. We need the first term, we need the ratio, and also the nth term we are looking. So the first 5. So our n will be 5. So let's see. We have S5, so the first term is 4. 1 minus R, R is -3 from the common ratio. to the power 5 because we're looking for the fifth term. So n is 5. Divided by 1 minus r. R is minus r. So here we do arithmetic operation. 1 minus 3 will give me 1 plus 3, which is 4. And negative 3 to the power 5. Again, 5 is a odd number. So our answer will be negative. 3 to the 5th will give us 243. Negative will give us positive. So we get 1 plus 2, 4, 4. The 4s here will cancel each other. We have 4 at the top, 4 at the down. They cancel, and we get 1 plus 2, 4, 3. So our final answer will be 244. Now the B, we know that we are looking for 6, the first 6. So n is 6. And the question gave us the first term to be 1/4. The common ratio is half. So we have all the values we need. We need the n, the first term, and the common ratio. So the first term, 1/4, 1 minus, the common ratio is half, to the power n is 6, divided by 1 minus, again, the r, which is half. So by doing the arithmetic operation, half to the power 6 will give us 1/64. Then quarter, 1 minus half will give us half. Then next, we multiply 1/4 divided by half will give us 2. Then we do our common ratio addition here. We get 6/4 minus 1/28. And that will give us roughly 63 by 128. So that will be the conclusion for our lectures in chapter 6, section 2. Chapter 6, section 2. In this chapter, again, we went through the concept of finding, again, compounded interest, and also in different periods, including the continuous compounded interest, and also geometric sequences. So again, if you have any question, post it in the Blackboard, or when we meet in class, again, we can discuss it. Thank you for your time.